This QuickLearn Bullet teaches you what is meant by a bond's convexity and explains why it is important to take this convexity into account when estimating a bond's price changes for large movements in yield. We start with a brief refresher of duration and modified duration, as these two concepts will help you better understand and visualize the importance of convexity when estimating a bond's price changes for large movements in yields. You can think of duration as the time it takes the owner of a bond to receive in present value terms half his original investment back, without differentiating between coupons and principal. Duration can be calculated via the following formula here. On the other hand, modified duration is simply duration divided by 1 plus the yield over the frequency of payments per annum. This means essentially that you take duration and discount it for one period at the applicable yield to obtain modified duration. Also, modified duration gives us a first-order approximation of how much, in percentage terms, a bond's price will change given a small change, upward or downward, in its yield. If a 6% bond's modified duration is approximately 11.31, for example, it follows that a 1 basis point change in yields will cause an approximate percentage change in price of 0.1131%. And it also follows that a 10 basis point change in yields will cause an approximate percentage change in price of 1.131%. More generally, we can write that the percentage change in price equals minus the modified duration times the change in yield, the minus sign reminding us that there is an inverse relationship between yield movements and price changes. Technically speaking, modified duration is closely related to the first derivative of the price equation with respect to yield. You will notice from this table here that as we allow yields to move by significant amounts from the original yield level of 8% in the middle row, we find that our linear approximation for the bond's price changes becomes increasingly inaccurate, suggesting a curvature in the actual shape of the real graph. This curvature in the shape of the graph is known as convexity. We illustrate the concept of convexity using the graph appearing here. Note the difference between the estimated price using modified duration and the actual price in red using the PV function when yields deviate significantly from their original level of 8%. We can calculate convexity using the following pretty ugly formula here. And once again, the mathematically gifted may have realized that convexity is derived by differentiating the formula for modified duration, once again with respect to y, yield, which amounts to saying it is the second derivative of the price function with respect to yield. Assume we have an 8% 30-year bond with semi-annual payment frequency at a time when 30-year yields are themselves at 8%. We proceed to calculate its convexity using the above formula and find that it is around 214. It is not possible to understand such a number intuitively. It suffices to understand, however, that the greater the number, the more you should expect the correct graph for the bond's price-yield relationship to deviate away from the straight line representing the linear approximation involving only modified duration. Having developed an intuitive grasp of the equation for convexity, we proceed to use the number to improve our estimates of percentage price changes given a certain large movement in yield. We do this via the formula appearing now, which begins as before and then adds an additional term known as the convexity adjustment right after the plus sign that you see in the middle. Note that whether yields move up or down, the squaring of the yield change in the last part of the formula ensures that the convexity adjustment is always positive, which is a very welcome bond characteristic for a bondholder. While the bondholder will still have losses if rates rise, the greater the bond's convexity, the more the actual loss will be reduced by virtue of the convexity adjustment versus what it would have been under the linear approximation alone. And conversely, when rates fall and the bondholder has gains due to modified duration, those gains are magnified further by the convexity adjustment, with the more convex bonds experiencing the greatest magnification. On this slide here, we examine the effect of the convexity term in the above formula and verify that it improves the price change estimate versus our earlier linear approximation. It quickly becomes apparent from an examination that this time the accuracy of our estimate is almost perfect for up to a 100 basis point movement in yields up or down. And really, it continues to be very accurate even when the yield movement reaches 200 basis points, again, whether up or down. We conclude by asking how a bond's convexity may be affected by the normal three variables, namely the coupon, the tenor, and the yield to maturity. Relationships can be summarized in this table here. As the tenor increases, duration, modified duration increase, and so does convexity. As the tenor decreases, duration, modified duration decrease, and so does convexity. As the coupon increases, duration and modified duration decrease, as does convexity. As the coupon decreases, duration, modified duration increase, as does convexity. As yield levels increase, duration and modified duration decrease, as does convexity. And finally, as yields decrease, duration, modified duration, and convexity all increase. You will have noted that for each row in the table, the same exact result holds for both duration and convexity. This should make it easier to remember. This concludes this QuickLearn bullet on bond convexity.